Welcome to this lecture series in number theory. We are starting a new module which will be about primes, and we will discuss at least these four things in this particular module. So we will be doing the fundamental theorem of arithmetic, which is a very basic result saying that any natural number greater than or equal to 2 can be written in essentially a unique way as the product of primes. And we will be doing Fermat's little theorem and Wilson's theorem, two very classical results in modular arithmetic. And then we will do special cases of Dirichlet's theorem. Let me not spoil what this theorem is. We will be doing very baby cases of it. This is a very, very interesting and beautiful result due to Dirichlet, but it belongs not in the realm of elementary number theory, even though I think elementary proofs are known. It belongs in analytic number theory. All right, so let's start. Let's recall what is a prime. We have already seen the definition before, and I'm sure you knew this definition from high school, but there is no harm in repeating. So a natural number at least 2 is said to be a prime if the only positive divisors of n are 1 and n. Right, so that's a prime number. And here is the definition of a composite number. If you have a number at least 2, it is composite if it is not prime. All right, and I haven't still figured out if 1 is counted as a composite number. It is certainly not a prime number, but I don't know if it is counted as a composite number. Just Google. A very important remark is the following. Suppose I have some natural number at least 2, then it has a prime divisor. Then K has a prime divisor. It's a very simple thing. If K itself is a prime, then nothing to be done, right? Because you can take K itself as your prime divisor. If K is not prime, then you write K as the product of two numbers, both of them greater than or equal to 2, right? If it is not prime, then it is composite. By definition, since it is at least 2, then it has some non-trivial positive divisor. It has a positive divisor in this range. Let's call A a positive divisor, which satisfies this inequality. So naturally, B will be at least 2. If B were 1, then A would be equal to K. So then you write K as the product of two things where both of them are greater than or equal to 2, but both of them are smaller than K. And thus, you can inductively now deduce that at least A or B, either A or B, has a prime divisor. In fact, both A and B have prime divisors by induction, because both of them are lesser than K. And that's it. So I don't want to explain this further. It's a very simple remark. I'm sure you follow. And now let's look at two other remarks that we have already proven before. So this is the first one. Suppose we have a prime P, and suppose it doesn't divide some given integer n. Then P and n are relatively prime, and that is what I have written in blue. I mean, I have written it in the language of invertibility, etc. But really what I wanted to say is that P and n are relatively prime. If P doesn't divide something, and P is a prime, then it is relatively prime to that thing it doesn't divide. It's a trivial remark. But by Bezout's theorem, then it says that there exist integers x and y such that px plus ny equals 1. That is the non-trivial thing, which is written in blue in just the language of invertibility. It's the same thing as the statement. Anyway, I'm sure we know all of these things by now. And one more thing I want to again stress, which we have seen earlier, is that if P is a prime, and suppose P divides the product of two integers, a and b, then P divides at least one of those two integers. Why is that? Well, if P divides A, great, we are done. If P doesn't divide A, then P is relatively prime to A. But then you can apply the dropping property. If P and A are relatively prime and P divides A times something, you can just drop A and say that P divides the something. That's it. That's the proof. So these two things are very important, but we have seen them ad nauseum by now. And now let's move to some more interesting things. I mean, these things are also interesting, but whatever. Okay, so this is probably the most classical result in elementary number theory, that there are infinitely many primes. And it's a non-trivial result. Okay? So the proof that I'm going to give is due to Euclid or a variant of that proof, but we should know that there are infinitely many proofs of this result. And if you Google, you can find them easily. There is even one proof using general topology, to my surprise, but whatever, I've covered that in my lecture series on general topology. Okay, so let's look at Euclid's proof. Fix some natural number n, and we will show that there is a prime exceeding n, which will finish the proof, right? So consider the proof goes by constructing a number which will do the job. So consider x defined as n factorial plus 1, where recall n factorial is nothing but the product of the first n natural numbers. Great. And since this number is at least 2, right, x is at least 2, there is a prime divisor of it. So let's say p is a prime divisor of x. And we claim that p is strictly greater than n. Okay, why is that? So to prove this, assume on the contrary that p is at most n. But if p is at most n, then p divides this number. So assume on the contrary. Assume on the contrary that p is at most n, and hence p divides n factorial, because n factorial is precisely the product of all the things which are at most n. So we have that, and therefore p divides the difference of x and n factorial. P divides x, p was a prime divisor of x, p also divides this guy, so we deduce that p divides 1. Which is a contradiction because p is a prime. It cannot divide 1, it is greater than 1. That's it, that's the proof. What a simple proof proving fairly non-trivial result. It's not obvious. Alright, let's move on to more interesting propositions. Yeah, this is also very nice. Fix a natural number n. We want to show that there exist n consecutive integers, none of which are primes. So there are arbitrarily large gaps in primes. That is what this proposition is saying in simple English. Let me write that down. There are arbitrarily large gaps in the set of primes. This is what we will prove. Again, this is a very nice, simple, short proof. I encourage you to pause the video and think of your own proof. There may be infinitely many ways to do this also, but I think I'm conditioned. I've seen this, so I am conditioned to think of only one way, which is as follows. So consider the numbers n factorial plus 2, n factorial plus 3, n factorial plus 4, and so on up to n factorial plus n. And we claim that none of these numbers are prime. None of these numbers are primes. I don't know if should be a primes or a prime. That's a problem with my English, but you understand. So what we will have shown once we do this, these are how many consecutive numbers? These are n minus 1 consecutive numbers, which we will have shown that are not primes, are composite. And hence this proposition will be proven because n is some arbitrary natural number. So this is all that we want to do. Okay, but clearly note that, to prove this, note that if k is between 2 and n, then k divides n factorial plus k. Right? Why is that? Because this implies that k divides n factorial, and k anyway divides k, so it also divides the sum of the two things. So k divides n factorial plus k, and hence n factorial plus k cannot be a prime number because it is greater than k, right? It is greater than k and admits a non-trivial divisor. It admits a positive divisor which is greater than 1. So that's it. So this cannot be a prime. I don't want to write anything more. That is the proof. So there are arbitrarily large gaps in primes. Okay. Now for probably the most interesting proposition of this lecture. We want to show that polynomials cannot generate primes. So what is the precise statement? Fix a natural number, n, at least 1, and suppose we have these integers. These n plus 1 integers are given to us, where the last one is positive. You could also take the last one as negative, but doesn't change anything, just take it to be positive. And define this function which consumes a whole number and outputs an integer, defined as follows. Right? This is for all x, obviously. Such a thing is called a polynomial. Right? I'm sure you knew this before, but anyway, so this is a polynomial with integer coefficients where the last one is a natural number. Okay, so we want to say that this function cannot always output prime numbers. Well, it will be outputting negative numbers for some time at least, or it could potentially output negative numbers. That is the correct statement. It is possible that it outputs negative numbers, and well, negative numbers we don't want to call them prime, so that's kind of a silly obstruction, so you might take the absolute value. Right? So we will just say that there is some k for which this is not a prime. In fact, we will show that there are infinitely many such k's. So the content of the proposition should be clear. It is a natural question to ask. Can you generate the set of primes via some simple function? Of course, you can say that let f be the function whose output at the kth integer is the kth prime. Well, that's a function, but that doesn't give us a recipe to construct that function using simple functions. And what are the simplest functions? The simplest algebraic functions are, the algebraic functions are polynomial functions. And it's just that using polynomials you can't generate primes. It's a natural inquiry. In fact, I think it was believed at one point that maybe by not very serious mathematicians, but I think people did believe at one point that this could be done. I should look up the history of it. Anyway, it's not a hard proof that we are going to give, and I encourage you to pause the video and think of your own proof. That would be the best. All right. So, okay, before we proceed, here is this one simple fact, which I don't want to justify, or not write a formal proof of. So note that there is some natural number n such that fx is positive for all x exceeding that natural number. It's in fact a weak statement. What you can do is show that fx becomes arbitrarily large. The value that the polynomial takes will become arbitrarily large. And let me just say why that is. So the point is that this guy is positive, and since here you have the power n, everything else will be dwarfed compared to this particular term if x is large. X will beat, this term will beat every other term relative to it if x is very large, and this of course grows without bound. The proper way of proving this is the following. Just note that fx can be written in this fashion. Fx is You take x to the power n out. If x is non-zero, you pull it out. You get an plus this divided by x plus a1 by x to the n minus 1, I think is what you will get, yeah. And then a0 upon x to the power n. And if x is very large, all of these numbers are very small. So you can kind of ignore them. And thus, only this much will matter, and that will grow without bound. So that is what I want to say, but I have written a very weak statement. Anyway, so whatever. Now let's continue. So we want to show that there is some k for which fk is not a prime. And to do that, first let t be some natural number such that ft is greater than 1. So this is what I kind of wrote here. This is not exactly what I wrote there, but whatever, I justified it here. So there is some positive t for which this will happen. This is bound to happen. Okay? And say, in fact, let's call this value capital K. Or maybe call it capital T, I think will be a better notation. I don't know. All right. And let P be a prime dividing T. Maybe I'll not call it T. Let's just keep it like that. Let P be a prime dividing Ft, dividing f of t. And yeah. So great. And here is an exercise for you. Horrible. Still horrible. If A is congruent to B mod n, mod P, then Fa is congruent to f of B mod P. It's very easy. Okay. And this has really nothing to do with the primality of P. Any natural number here will do. Alright, so let P be a prime dividing f of t. And now define x naught as t times p plus 1. Okay. All right, and now using this exercise, we know since x naught is congruent to t mod p, we have fx naught is congruent to ft mod p, right? Which implies P divides f of x naught. Okay. In fact, here is what you can do. Define x sub r be t times pr plus 1. Then P divides f of xr by the same reasoning. Right, because this is also congruent to t modulo p. Now, this is an increasing list of natural numbers. If you vary over r, going from 0, 1, 2, 3, this is an increasing list of natural numbers. And all the values that f takes on those numbers, all of them are divisible by p now. And therefore, as we said, this grows without bound. The value that the polynomial takes on arbitrarily large numbers is also arbitrarily large. This will take bigger and bigger values for very large values of r, and hence at some point it is bound to be not prime because it has a non-trivial divisor which is fixed. Right? At some point this is going to grow bigger than p. And when that happens, we know that this is not going to be prime because it is divisible by p. It cannot then be equal to p. Great. So that's a proof of the fact that polynomials cannot keep generating primes, but I'm sure there must be many other ways of seeing this. I think this is also pretty simple. I don't know how else to explain this proof. You just by hook or by crook create something, I think it's a fairly natural proof. You can examine it if it eluded you. But yeah, it's a very important or very nice puzzle, if you will. Okay, another puzzle. This is another attempt to generate primes. Suppose we consider such numbers, let's say. Can you find, is it possible that this is always prime? In fact, what we want to show is that this will not be prime infinitely many times. That's what I've written here, that it will be composite for infinitely many values of n. Okay? So let's see how we do that. I mean, again, I encourage you to pause the video and try to find your own proof. There are at least 2 ways of doing it. There should be more, but here is the proof that is natural to me, and then I'll show you another proof. The point is, the thing that motivates the proof is the following. The sum of these 2 numbers is 13, and that kind of jerks me to think that maybe I can always make it divisible by 13, or maybe I can make it divisible by 13 for many values of n, and hence we will have shown that all of those numbers are composite. And that's what we will do. So here is the proof. We know we see that GCD of 10 and 13 is 1, since 10 is relatively prime with 13. We know that 10 has some order modulo 13. We know that there is some natural number. We'll write that as capital N, such that 10 to the power n is congruent to 1 modulo 13. In particular, you can take this thing to be as take this thing as the order of 10 modulo 13. But any such natural number n is enough for our purposes. So this implies that 10 to the power n plus 1 is congruent to 10 modulo 13, which implies 10 to the power k times n plus 1 is congruent to 10 modulo 13 for all k. And thus, this thing plus 3 is congruent to 13 modulo 13 for all k, at least 1. And this I can write as 0, which implies that 13 divides. Right, and therefore, infinitely many of them are not prime. In fact, all of them are greater than 13, and hence none of them are prime. They have a divisor 13, but none of them are equal to 13. So none of them are primes. That's it. All of them are composite. But the other proof would be, another proof would be that you can just show that 7 divides 10 raised to the power 6k plus 4 plus 3. This you can show for all k. So it's a similar proof in spirit, but I think the most natural way is just to observe that 10 plus 3 is 13 and just try to show that 13 always divides this guy. That's probably the most natural way. But yeah. Right, so you cannot simply generate primes. There doesn't seem to be any simple algorithm which always outputs primes. But there are some. You can find even YouTube videos where they construct a function using trigonometric functions, maybe greatest integer functions, etc. and they are able to generate primes using them, but they are not efficient. If you use those functions to generate primes, it will not be computationally efficient. Okay. So with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.